So in this tutorial, we're going to start using multi-model ensembles. So one question you might ask is, why are there so many Earth system models? Why don't we just have one perfect model? Now, we already introduced the idea that models don't exactly reproduce the real climate because of internal climate variability. We could never know what's happening everywhere in the atmosphere and ocean at a given moment in time in order to perfectly initialize climate model. So this variability will always impact simulations and cause them to diverge. But there are also other reasons that these models don't exactly reproduce Earth's climate, and that's because they're an approximation to climate. And there are many different models because there are different approximations we can make. There are different physics that we code into our models through parameterization. And there are different numerics and discretization schemes that we can use. And so in addition to the physical source of uncertainties for internal climate variability, there are these human scientist-driven choices that create uncertainty in a given model's projection. And we have a variety of models that make different assumptions about physics or the numerics or the discretization. And by creating a multi-model ensemble, bringing information from all these models together, we can quantify how much these different physics, numerics, and discretizations are affecting our model's ability to project the future. So we can gauge how these processes and differences are contributing to our uncertainty projections. And there are actually over 50 distinct Earth system models that are used in CMIP6, coming from about more than 30 institutions. And these institutions don't necessarily represent the whole global science community very well. In fact, there are some places that have some countries that have several Earth system models. But even within those Earth system models within one country, there are often big differences in the physics, numerics, and discretizations that are used. And so these models have a pretty diverse range of numerical and physical choices going into them. And we talked about the ingredients of an Earth system. We talked about how the grids can differ last week. We worked on regridding Earth system model data. We're not going to go into the algorithms and numerics, but we will talk for this tutorial slides a little bit about the physical assumptions that go into these models, the choices of parameterization and physical assumptions. So parameterizations are important because they're a way of representing unresolved or complex processes that are too complex or too small, fast to be modeled by an Earth system model. And a parameterization is a way of approximating the effect of a physical process through a simplified mathematical relation containing important parameters. That's why it's called parameterization. And these parameterizations allow us to approximate the effects of those processes without actually modeling the processes themselves, if they're too fast, too complex, too small to be modeled practically in simulations. And you've already encountered some types of parameterization. Last week, you looked at energy balance and you modeled the Earth system's energy balance through a relationship something like this, where you assumed that the atmosphere transmits a fraction tau of outgoing radiation. And that tau is really a parameterization for much more complex and detailed physics that are going on within the atmosphere. We know that the chemical constituents that absorb and emit radiation in the atmosphere have varied. There are many different constituents that absorb different wavelengths of light, and each of these constituents has different vertical distributions. So the absorption of light differs between wavelengths and heights in the atmosphere. And so this tau is trying to represent a lot of complexity in a relatively simple form. Now, to understand the kinds of things that have to be parameterized in a typical Earth system model, we can look at how the resolution and complexity of these Earth system models and climate models have evolved over time. Basically, they're becoming higher resolution and more complex, but still our Earth system models typically only resolve things bigger than about 100 kilometers. But they do now include a lot of complexity through the form of things like atmospheric chemistry and biogeochemistry in the ocean and aerosol and cloud physics, and more detailed land use and cover impacts on the Earth system. But even with these advancements since the first IPCC report in 1990 and is denoted by the properties on the left, even in our most recent IPCC report denoted by the blue properties on the right, many important processes are still not resolved and need to be parameterized. So just to give you an example of some of these processes, we can look at what kinds of things are climatically important but smaller than 100 kilometers, the grid size of a modern Earth system model. To do that, I'm going to look at this map of the UK. If we look at how the resolution of models has changed since the first IPCC report, the higher resolution, denoted by the red boxes on the top, can clearly resolve much more detail than the lower resolution, noted by the box at the bottom here. But even so, there are things like the topography of land and the impacts that that could have on regional climate and weather that are unresolved, even at these 100-kilometer scales. So that the mountain ranges here are shown by red and are typically much smaller and more detailed than 100 kilometers. And there are things that are climatically important but smaller than 100 kilometers in the atmosphere, like clouds, and on the land surface, like the variations in surface conditions that can affect regional climate. In the cryosphere, things like icebergs and glaciers and ice shelves typically have dynamically important, physically important scales that are smaller than 100 kilometers. In the ocean, we get eddies. So this region is just off the southwest coast of this map of the UK. We can see eddies that are far smaller than 100 kilometers in size and are interacting with the biogeochemistry of the ocean. So not only are their physics smaller than 100 kilometers, there are climatically important biogeochemical processes that could impact the carbon cycle, for example, at these much smaller scales. And so we know that these things differ between Earth system models, and what you're going to do in this tutorial is take an ensemble consisting of multiple different models and their projections of the Earth system climate's future. And you're going to look at how this ensemble can tell you about the uncertainty that we have in those projections.